Welcome back once again. In today's lecture, we'll discuss concepts of similarity applied to biology. It has been claimed that the various organisms and physiological mechanisms operate similarly and governed by the same laws in different species. Therefore, various species may be treated as scaled model of the same machine, and that the various biological functions must be scaled following the rules of similarity. In this lecture, we will explore this concept using some interesting examples. At its simplest, we obtain that Kl is 1/3 power of Km. Simply because Km is like K rho Kl cubed, and K rho is 1. The tissue density is the same in almost all species, very close to 1000 kilograms per meter cube. So let us see what results. This is some published data about various animals. Tracheal diameters and the tracheal length. The diameter of the trachea, the windpipe, and the length of the windpipe. And is plotted against the body weight of animals. And we see, very interestingly, that for almost all animals, starting from bat to whale, the points lie almost on the same line. This for the diameter of the trachea and this for the length of the trachea. The scale for diameter in centimeters is here, and scale for tracheal length is here. The slope for diameter is 0.39 and for length is 0.27. Compared to our prediction of 0.33 using strict similarity. So over this whole region of a bat weighing less than 100 grams to a whale over 2000 kilograms, the trachea is scaled by mass raised to power 1/3. A very good agreement, I would say. This data is taken from this paper. A trivial but dramatic example. Determine the relation between scale factors for the weight of the animal and their surface area, the body surface area. From a scale factor relation, that should be relatively easy. If the length scale factor is Kl, the area scale factor is Kl squared, and the mass scale factor is like Kl cubed, assuming that K rho is 1, that is, the density of all mammals is about the same. Thus, the surface areas of mammals should vary like mass raised to power 2/3, or S is like M raised to power 2/3. And what is the data that we see? From this reference, we see the body surface area and the body weight are following this line. The red line has a slope of mass raised to power 2/3. Log plot. So that seemed to confirm our assertion. Stahl and Gemerson measured the dimension masses of some skeleton and organs of 5 different species of adult primates and fitted them to the equation x is equal to a m raised to power b. A and b are constant, and m is the mass of the primate. And this is what he obtained. He measured for a large number of individuals of 5 primate families and measured something like vertex to heel height, trunk height, chest circumference, thoracic width, all linear dimensions. And this is a question. If we try to fit our data, the value of parameters A was given here and the value of exponent B are given here. Since all these parameters are length, the theoretical exponent B should be the value of 0.33. And you see these values are very close to 0.33. Similarly, the skeletal length, humerus, radius, ulna, femur, and fibula for 5 different species, and fitted the data to this equation and obtained these values A and B. Again, the exponents are very close to the theoretical exponent of 0.33. Skeletal weights in grams. These are the fitted value of the exponent and the expected value of the exponent if we assume complete similarity. And similarly, for organ weights, pretty good agreement, I would say, tends to confirm what we started out with. Now we go to another example to a different domain altogether, the allometric analysis of trees. Here in this graph is data of the diameter of the trunk of the tree, a length, versus the height of the tree, the crown radius of the tree, the number of leaves, and the biomass. We obtain pretty good agreement. The height and the crown radius, this line and this line, a length scale. So they should be linear with the diameter of the trunk. Here we see the power is 0.80 and 0.87. Not a very good agreement, but quite there. The biomass is density times the volume, and the volume should be 3 lengths, and we get 2.82, quite close to 3. And therefore, this confirms that trees are also quite similar. Let's extend this analysis a little further. The human weightlifting capability are taken data from the weightlifting championship, the World Championship of Weightlifting last year. How much weight can a human being lift? Obviously, there must be the same kind of stress, the maximum stress in the muscles that a well-trained human being should experience. And so the force that a muscle could apply would be like stress times the area. And if stress scale factor is 1, the area scale factor is like length squared. And so the weight lifting capacity should be like the mass of the subject, mass of the human being raised to power 2/3. To repeat, if it is argued that the maximum stress level in the muscles of all persons is same irrespective of the size of the individual, then K mass of the individual is like KL cubed, and the KW, the weight lifted, is like K of area, K stress being 1, And so KL is like KL square. So the scale factor for the weight lifted, KW, should be like the scale factor of mass raised to power 2/3. Let us look at the data. World men weightlifting records as of July 2020. Weight lifts versus weight of the lifter. Weight of the lifter here and weight lifted. These are the records. And you see there is a pretty good agreement with this line. These are the records in the weight class 55 kilogram. The total lifted weight in kilogram was 294. So the weight of the individual raised to power 2/3 divided with the weight lifted, it comes to 0.0492. For the 61 kilogram weight class, it is this. So this ratio is increasing only very slightly over this range. The lowest value is 0.0481 and the highest value is about 0.0530. This line is a plot of m raised to power 2/3 divided by weight. This appears to justify our assertion that the weight lifting capacity can be predicted from mass raised to power 2/3 of the individual. Similar data for women weightlifting records. Here, mass raised to power 2/3 divided by weight has a higher value, but the values are almost the same across the weight classes. This higher value means that the maximum stress level in women is slightly less than the maximum stress level in men, but doesn't take away from a basic proposition. Scale factor breathing rates. Consider the metabolic rates in mammals. This rate should depend upon the rate of heat loss. The metabolic rate should be enough to supply the heat being lost. And the heat loss is in turn proportional to the surface area of the mammal. If all the organs of mammals are assumed geometrically similar and are made of similar material, what is the scale factor of breathing rates in terms of Km? The scale factor of mass. Now to determine that, let us consider that the breathing rate would depend upon rate of metabolism. That is the amount of heat that is being produced in the body. The heat produced in the body must be equal to the heat lost by the body. And if the temperature differences are of the same order, then the heat lost would be proportional to the surface area of the body. And so the heat produced must also be proportional to the surface area of the body. That is like KL squared. Now heat is produced by oxidizing food. So the scale factor of heat produced is the same as scale factor for food consumed, the mass of fuel consumed. The mass of food consumed would be proportional to the mass of oxygen that is used for oxidizing that food. So the mass of oxygen per unit time should be like KL squared. This is the same as the scale factor for the surface area. So scale factor for need of oxygen must be same as scale factor for area. Since the scale factor for the volumes of the lung would be like KL cubed, so the scale factor for the breathing rate will be KL square by KL cube, or 1 over KL. So if K rho is 1, KL is Km raised to power 1/3. And then the scale factor of the breathing frequency would be like 1 over Km raised to power 1/3, or Km raised to power minus 1/3. This is the scale factor for breathing rates. The heavier the mammal, the lower would be the breathing rate with the power of 1/3. If the mass is 8 times, the breathing frequency would be 1/2. The Lilliputians and the Bobigdinians of the Gulliver travel frame differed by height ratio of approximately 1:144. The Lilliputians was 1:12. A foot was like an inch. And same scale between Bobigdinians and humans. Let us estimate using biological scaling their relative masses, frequencies of breathing, velocity of walking, and the maximum jumping height. Treat the Lilliputians as the models and the Bobigdinians as prototypes. So KL is 144, 12 raised to power 2. Mass scale factor Km would be K rho KL cubed, and that would be about 3 million. The mass of a Bobigdinian was 3 million times the mass of a Lilliputian. We have already calculated the scale factor of frequency of breathing for warm-blooded animals, and that is 1 divided by KL. So it would be like 6.94 into 10 to the minus 3. Walking velocity. The scale factor of walking velocity would be same as scale factor of any other velocity, which would be KL by KT. And KL by KT would be KL into KF. KF is the frequency. KT is 1 over KF. And we have seen just now that KF is like 1 over KL. So K for walking velocity is 1. So the speed at which the two species walk would be about the same. To calculate the scale factor of jumping height, assume that the maximum stress level in all species are the same, so that the maximum work done by muscles in jumping is scaled by K work, which is K force into KL. And K force is like K rho, KV square, KL squared. So K work becomes K rho, KV square, KL cubed. The work done is converted to potential energy in the jump, so that if H is the height jumped, K potential energy is like K mass into Kg into Kh. And so it gives you KL cubed, Kg, Kh. Equating this to K work, we get with Kv is equal to 1, we get Kh is equal to 1. So that the two species can jump up the same height. Interesting. Which species would have more difficulty with the surface tension of water, with the viscosity of water, and with the Earth gravitational field? Consider the ratio of the inertial forces to the forces of surface tension. Inertial forces are like K rho, KL square, KV square. The surface tension forces scale factor Kf sigma is like K sigma KL. From this, we get the ratio of the two forces. The surface tension forces to inertial forces is 1 over KL. or 1 by 144. So the prototypes Barbarians with less difficulty with the surface tension. The larger the L, the less significant is the surface tension. Ratio of the viscous to inertial forces is like 1 over Reynolds number. And here, this turns out to be 1, so that the two population would have the same difficulty with the viscous forces. Let's do this last example, a very interesting example. David Hu and his co-workers report the discovery of law of urination, according to which all animals ranging in size from mice to elephant empty their bladders in nearly constant time interval of 21 plus minus 13 seconds. There's variation, but there's a random variation. Independent of their sizes. So that the time that they need to empty their bladders is about the same independent of the size from a mouse to an elephant. We are not sure what are the dominant forces controlling the urination. Is it gravity and inertial forces? The gravity which accelerates the flow downwards, the inertial forces that need to be overcome. Gravity and viscous forces. Gravity, the accelerating force, and viscous forces, the resistance that need to be overcome. Or the elasticity of bladder and the inertial forces, or the elasticity of bladder and the viscous force. Let's examine these 4 pairs. Let's first look at the pair gravity and inertial forces. The scale factor of gravity force is like scale factor of mass times the scale factor for g, acceleration due to gravity. So that's like k rho kl cubed kg. For the inertial forces, we have determined very large number of times is k rho kl square kb square. So if these are the two forces of concern, then kl kg should be like kv squared. Kv squared would be like kl squared divided by kt squared. And so this gives g tau square by L is constant. Or that the tau characteristic varies like under root LC by G. So clearly this is not the pair that determines urination, because Tc is independent of Lc. Observed fact. But if gravity and inertial forces were the controlling forces, then Tc should vary like under root Lc. So incorrect. Let's look gravity and viscous forces. Scale factor for gravity forces again k rho kl cubed kg. And for viscous forces, as determined before, is k mu kl kv, which gives k rho kg kl square must be k mu kv. And from this, we get tau rho gl by mu should be constant, and which results in tau being inversely proportional to Lc. So this again is not a valid pair of forces controlling urination. Let's look at the third player, the elasticity of the bladder and the inertial forces involved. Elasticity would be Ke times area KL squared, and the inertial forces, of course, K rho KL square Kv square. And so this yields Ke is like K rho Kv square, and which gives you rho V square by E is constant. From this, we get TC is directly proportional to LC by rho E. So this also is incorrect. Let's look at the last pair now. Elasticity of bladder and viscous forces. The scale factor of elastic forces is Ke KL square. For the viscous forces, K mu KL KV. And this gives Ke KL is equal to K mu KV, which gives you tau E by mu is constant. Or tau C is mu divided by E. We are talking of the same urine almost. K mu is 1. Elasticity of all fibers, muscle fibers should be same. So K capital E is 1. So the only valid law which is independent of LC is this. So it is the elasticity of bladder and viscous forces that control urination. We can construct models for this and analyze further. We have in this lecture covered a few examples of applications of scale factors to biological systems. I hope you enjoyed them. Thank you.